Welcome back, Virtual Precalculus. In this section, we really get into the meat and potatoes of determining probabilities. The book makes a little point that there are sort of three kinds of probabilities. There's the actual probability of an event, which we can never really know. It is whatever it is. If you believe in some sort of higher power, then I suppose that's the only sort of being that could understand and know exactly what the probability of some sort of uncertain event might be. But there are also experimental probabilities, which we can measure by having an experiment, conducting trials to test how probable events might be. And then there are theoretical probabilities, and we can use counting techniques and the fundamental principles of counting and probability to determine those. But both experimental and theoretical probabilities are always approximations of any actual real-life probability. Experimental probabilities, like I said, are determined by experiments or trials. And the most important thing about conducting these kind of experiments is the fundamental rule is sort of that the more trials you conduct, the better estimate of the true underlying probability you actually have. For example, example 1 in your text in section 13.4, you're looking at 200 trials of throwing a dart at a dartboard. And you hit the red part 43 times, the yellow part 86, and the blue part 71. So if you can calculate the probabilities as the ratio of times you hit the red to the total number of trials you had, then that would be the probability of hitting red, and that comes out to be roughly 20%. Probability of yellow, calculated in a similar way, is about 40%, and the same for the probability of blue. Now they're not exactly the same, yellow and blue, and if you wanted to know better which one was more likely, you'd have to conduct more trials, maybe 300 or 400. But that does illustrate the basic law of probability, which we are going to use a lot in calculating theoretical probabilities. You've heard me refer to this law as happy over total, which is the way I think about it. More formally, you can say that the probability of an event E is equal to the ratio of the number of outcomes in that event to N, which is the total number of outcomes in the sample space. In other words, it's equal to the number of ways that the event can happen divided by the total number of things that can happen. So with the darts, we divided 43 times that we hit red by 200 times that we threw the darts. All right, simple example to illustrate that. Example 3, you're going to roll a number cube. In other words, a die, six-sided cube with a number on each face that's unique. And the chances of getting 1 or 2 or 3 or 4 or 5 or 6 are all the same. It's just 1 out of 6 because there's one way that the thing can land for you to get any particular number, say 4, and there are 6 ways that it can land total. So happy over total, I'm happy if I get 4, and the total is 6, so there's one way to get 4, there's 6 ways for the thing to land, so 1 over 6 is the probability of getting any particular number that you might want. The probability that you get an even number, well, slightly more interesting. How many ways are there to do that? That's right, there's 3 ways to get an even number, 2, 4, and 6. 3 ways out of 6, 3 out of 6, or 1 out of 2, 50% chance of getting an even. All right, so that's the simple fundamental probability principle. Another slightly more interesting example, we're going to toss a coin 3 times. Each time the coin can land heads or tails. And we can look at the probability that we get no heads in those 3 trials, 1 head, 2 heads, and 3 heads. Okay. Here, I've listed all the possible outcomes in the sample space. There are 8 of them, right? I think I caught them all. And then the number of outcomes that have only heads, all 3 heads, right? That's just this one here. There's only 1 like that. These 3 here have 2 heads. These 3 here have 1 head, and this one has none. Okay, so to compute these probabilities, one way to do it is to divide the number of outcomes for each event. For example, no heads, there's 1 outcome. Divide that by the total number of outcomes in the sample space, 8. So 1 over 8 is the probability of getting no heads, 3 over 8 for 1 head or for 2 heads, and 1 over 8 for 3 heads. Your book does this in a slightly different way. And it's interesting to look through the way they did it. It sort of brings up some principles we discussed last week. As you know from last week, to find the probability of a compound event involving AND, meaning both things have to happen, you multiply the probabilities of the individual events, as long as they're independent events. And for an OR, compound event, you add them as long as they're mutually exclusive events. So in this case, the events are both independent and mutually exclusive. The tossing of one coin does not affect the tossing of a second coin, and a coin can only either be heads or tails. It can't be both. So the events are independent and mutually exclusive. So the way the book does this is they say, look, the probability of 3 tails, or no heads, is the probability of the first tail, 1/2, times the probability of the second, times the probability of the third, which comes out to 1/8. And that's good, because that's exactly what we got the other way. So to do another more complicated one, like say for one head, well, there are 3 ways to get one head, right? You can get heads, tails, tails, or plus, you can get tails, heads, tails, or plus, you can get tails, tails, heads. And so we find the probability of each of those 3 in the same way that we did for tails, tails, tails. It's 1/8 in each case. And we add them because they're ORs and they're mutually exclusive. And we get 3/8. Once again, we confirm the results that we got my way. Okay? And you can do that for all the other outcomes in that problem. So there's always, there's often multiple approaches you can use that are, equivalent. You just need to figure out which way works for you and make sure you use all the right tools in the right situations. So now we need to learn how to count. I know what you're thinking. You think you know how to count. Well, maybe you do and maybe you don't. But we'll see in part 2. I'll see you there.